Okay, so we shall start with the discrete time signals as discussed in the last class. So a discrete time signal we shall represent by this mathematical notation where it's a sequence of the variable x with respect to the time instant n, where we have n varying from minus infinity to infinity. So sometimes we shall represent or we shall use the notation like this, or sometimes we use the notation by this. Okay, either with the square brackets or with the ordinary brackets. The point to be noted here that n is an integer. So given an analog signal, let's say we represent that analog signal as xa of t. So when we do the sampling at time t, we just get the signal x of n, which can also be represented as x n times t, where n is the nth sample of the sequence. Or sorry, x of n is the nth sample of the sequence. So now we shall see the basic types of signals, and then we shall see the processing of those signals. So the first type of signal is unit sample signal or sequence. Okay, so this sequence is denoted by delta of n, as it would be 0 for n not equal to 0, and it will take the value 1 whenever you have n is equal to 0. We also call it the discrete time sequence or discrete time impulse, or simply the impulse signal. So the nice thing of studying this signal is, say for example, you are given any signal which is represented or which is illustrated by something like this. You have the 0, so this is some signal which is illustrated by this figure, where we have the x-axis n as a discrete time axis 0, 1, 2 up to infinity, and at time t or n is equal to 1, the value of the signal is a1. Here at a2, and here at the 7th sample we have the value a7. Similarly, at the sample minus 3, we have the value a minus 3. So we put into the subscript the nth sample. So if we want to represent the signal, this sequence or this signal can be represented as by p of n, where this signal of is some pn. So pn would be a minus 3 delta times n plus 3 plus a1 delta of n minus 1 plus a2 delta n minus 2 plus a7 delta n minus 7. So if you see the property of this signal, that this signal takes value 1 at n is equal to 0. So this term will be 1 when n is equal to minus 3. Otherwise it would be 0. Similarly, this would be 1 at n is equal to 1. this term would be 1 at n is equal to 2, and this term would be 1 at n is equal to 7. So this is how we can represent a sequence using this unit sample sequence or discrete time impulse. Uh, Now another compact way of representing such kind of sequences or the signals as x equal to n, for k is equal to minus infinity to infinity x of k del n minus k. Okay, because it would be a summation where only at n is equal to k, the nth sample will take its value. Okay, and the k varies from minus infinity to infinity. The second type of sequence is unit step sequence, which is mathematically represented by u of n as equal to 1 when n is greater than or equal to 0. It takes value 0 for n less than 0. Okay, now if we want to establish a relationship between the unit sample sequence and the unit step sequence, it can be represented as u of n is equal to summation of k from minus infinity to infinity over del of k. Okay, now since we have this from minus infinity to infinity, and we know that it would be 0 for n less than 0, in compact way it can be represented as, it would be not up to infinity but up to time n. Okay, so summation of k is equal to 0 to up to infinity, we have delta n minus k. So both of the representations, they are equal. So what does it implies? If we see on the figure, we have this starting from 0, it takes the value 1, because it is a summation of all the values starting from k is equal to 0 to infinity of delta n minus k. So un is nothing but del n plus delta of n minus 1, delta of n minus 2, and so on. Okay, so this is an important equation to note. The third type of sequence is exponential sequence. So such kind of sequences are denoted by this equation: x of n is equal to a into alpha to the power n. Now, with respect to a and alpha, you can represent multiple types of signals, or this exponential sequence exhibits different properties. So if a and alpha are real numbers, then the sequence would be real. The second condition, if we have alpha lying between 0 and 1, and a is a positive number, then this sequence, or then the sequence values, are positive, and the values will decrease with increasing n. This you can also visualize by a simple coding in the MATLAB. Now, if alpha lies between -1 and 0, in that case the sequence values will alternate in sign, but the magnitude will decrease with the increasing n. So, but uh, decrease in magnitude with increasing n. Okay. The next condition is that if alpha is a complex number, in that case, you will get the sequence which is denoted by exponentially weighted sinusoids. So if both the alpha and a are the complex numbers, in that case they can be represented as if by using the polar form of the complex number as alpha is equal to the magnitude of alpha e to the power j omega naught, and you have a as mod a e to the power j of phi. Okay, so let's see the signal what we have initially, a alpha to the power n. So substituting the alpha here and a here, we get mod a e to the power j phi times mod alpha n e to the power j omega naught n, which can be further simplified to mod a times mod of alpha to the power n e to the power j omega naught n plus phi. So this is in the polar coordinates. In the rectangular coordinates, it can be written as mod a mod alpha to the power n cos omega naught n plus phi plus j sine omega naught n plus phi. Okay. Now if we have alpha or mod of alpha in the above equation greater than 1, then this sequence will oscillate with an exponentially growing envelope. The sequence oscillates with an exponentially growing envelope. On the other hand, if you have mod of alpha less than 1, in that case, sequence oscillate with an exponential decaying envelope. Okay, so many times we say omega naught as the fundamental frequency. We will talk about it later in the course. And your phi is the phase. So in the discrete time sequences or the signal, one of the question arises that do we need to analyze the sequence at all frequencies if we want to process them by through some system? Does it require to analyze the sequence at all the frequencies? So the answer is no. So let's see why. First of all, let's see the complex exponentials with frequency omega naught plus 2 pi r. Complex exponentials with frequency of omega naught plus 2 pi r, where r is also a belongs to a set of integers. So If we see this complex exponential with frequency omega naught plus 2 pi r, and we know it goes to the power of the exponential, so the signal for the sequence at frequency omega naught and at omega naught plus 2 pi r, they are indistinguishable from one another. Meaning to say it is the same signal. We can verify, say for example, we have x of n. If we write cos omega naught plus 2 pi r, where I just replace omega naught by omega naught plus 2 pi r, n plus 5. So you will see by using the property, it will give you this cos omega n plus 5. Okay, so that's why we are generally concerned with the frequencies lying between minus pi and pi to have the window of 2 pi, or we analyze a signal for omega naught lying between 0 and 2 pi. Okay. Talking about the periodic sequence, so we say that the sequence x of n is periodic if it satisfies this property where we have x of n is equal to x n plus some capital N for all values of n where n is an integer. Right? So for discrete time sinusoids, the one we had seen earlier, so if I replace the time index n by n plus n, so initially we saw that a cos omega naught n plus 5. So if I replace this, if the signal is periodic, so it should be equal at n. If I replace this n by n plus n, so a cos omega naught n plus omega naught capital N plus 5. So we should have this omega naught n should be equal to 2 pi k by using the above property, because we know that the signal repeats itself, where your k definitely an integer. Okay. And for complex exponentials, we have e to the power j omega naught n plus capital N, and it would be equal to e to the power j omega naught n if we have omega naught n is equal to 2 pi k. Right? The same condition we require whether we consider the discrete time sinusoids or we consider the complex exponentials. So this is all about the basic types of sequences. In the next class, we shall see the definition of the discrete time systems and some properties associated with the discrete time system.